And let's get started. So this is the first mechanical workshop. Welcome, cool mechanical folks. And this time we'll basically be talking about the engineering design process, as well as how to make block diagrams and mechanical plans. And then finally, we'll get a bit into fluid systems. So for those of you who are using any pump related things or fluid like tubing, etc., get a bit into that as well. All right, so this presentation was made with the help of William Tang's handbook to block diagrams and engineering design. If you guys are interested in looking at his handbook, I'll send the PDF later and there will be a link over here that you can click on. And he has some cool stuff there as well. So let's get started. All right, so before you guys start mechanically planning out your experiment, there's like 3 different things that you guys should consider. One is having sufficient research. And obviously, ideally, you should be looking at some research or review papers. And like we said in the last workshop, review papers really help you to go in depth. And it gives you a broad overview of most of the research that has been done in the area that you are studying. And it's important to understand how and why different things work. So even when you're making your mechanical plans, you can correctly model it and apply it. And for any sort of scientific idea, then you know that it will work with your experiment, or you know the basis behind it. And the second thing is having obtainable results. So when you're designing your experiment, is there any way that you can see that is there any way you can see your results, and are you able to measure it? If you're using only a camera, make sure that your results is significant enough or big enough, or the color is contrasted enough so that it's able to be observable. Another thing to consider is your camera can only take one picture every 7 minutes or 3 to 4 minutes, depending on the resolution you use. So is what you'll measure significant and slow enough such that you can actually get a picture of that. And ideally, you might want to have more than one sensor in case your camera fails, but this kind of depends on the team. I know some of your experiments won't be able to really use that, but it's a good backup, because sometimes the camera does fail, and then that just means you won't get any data for that year. So if there's any way that you can observe something with another type of sensor, whether that's I think some of you guys are using some sort of current sensor or light sensor, etc. Those are all good as well if you're able to implement it. And then finally, microgravity significance. So one of the most important things is, why are you sending your experiment to the ISS? So what does microgravity do that you can't do back on Earth? Whether that's microgravity affecting any properties of your experiment, or otherwise gravity causing your experiment not to be able to work on Earth. So those are 2 different things that you can kind of think about, and I'm sure that most of your experiments already consider this factor. And another thing is, how are you going to test this and compare your results in space with the results that you get on the ground? For example, our experiment last year was basically impossible to do on the ground, but we were able to figure out some sort of configuration such that it was possible to test. So make sure you can kind of compare between your ground test and then your flight test to see what significance does microgravity really have on your experiment. All right, and then here are some this design constraints for your mechanical. So keep in mind the power constraint of your microlab. You're only allowed up to 100 milliamps, and you're at 5 volts for each of your microlabs. So your microprocessor draws 40 milliamps. So effectively, you can only use up to 60 milliamps at 5 volts. So that includes all of your pumps, your camera. Whenever your camera's on, you basically can't turn anything else on other than your LED. So keep in mind, you don't want to go over that power limit, because then that also does draw away from the other experiments. So you shouldn't go over that limit. Okay, and then in terms of fluids, so you need 3 levels of containment. If you're working with anything that has any sort of liquids, your first level of containment would be your own chamber. So whether that's your waste bag or the chamber that you're injecting into, make sure that's sealed up and so that your liquid doesn't get anywhere near your PCB or it doesn't like leak out. And then your second level of containment would be your micro lab. And the third and final level of containment would be your nano lab. So those are the 3 layers to kind of make sure that your fluid doesn't leak out. And then third thing is, if you're using any sort of materials or biologicals, make sure you read and save all of the material safety data sheets for all of your chemicals and fluids that you're using. You'll need all of the data sheets for when you're filling out safety forms later on. So it's just good that if you're using something, just save it for now. So it saves you from a lot of trouble. And if you're using anything having to do with like living organisms, etc., there's a lot of really strict regulations on that, as Mr. O, I think, talked to you guys about earlier. So make sure to check with your mentors on that as well. And then for size, so keep in mind all of your components have to fit within 43 by 44 by 97 millimeters of your like very small micro lab. So anything that you're using. And also keep in mind that if you have any waste bags for liquids or containers for liquids, your wiring, your tubing, your PCB, these all also take up space. And your and your PCB kind of takes up a lot of space because there's like a space in between your PCB and the bottom of your nano lab. So make sure you keep those in mind. And also, if you guys really, really need more space, or maybe you need more power or something like that, there is a possibility that you can propose to have 2 micro labs. So if you come up with some sort of presentation that tells the mentors like why you would have to use 2 micro labs and what you would do with that space or what you would do with that power, that is a possibility that you can get 2 of them. And that does help a lot with your size and your power constraints, but only if you need it. And then field of view. So your camera has a very narrow field of view and also the depth of field. So it can only focus on things that are within a certain small range and also within like a small width as well. So when you're designing your experiment, you have to keep the placements of each component in mind, and especially of your chamber. Make sure nothing's covering it, and also that your chamber is small enough so that the camera can capture on what you want it to capture, and that the depth is not too big such that you can focus on what you want to focus on. It is possible for you to tilt your camera chip slightly, so your camera is kind of on another chip, and you can tilt it a tiny bit so that it goes like off to the center, but not by very much. So essentially your camera is just like stuck to that chip on the very bottom of your micro lab. But if you really need to move the camera, so this is just an idea, it is possible to attach your camera to wiring, to wires, and then you can move your camera to wherever you want it to. But that is very annoying and also kind of prone to wires breaking and all that. So it's not recommended, but if you really do need it, that is a possible thing that you can do. And then finally, complexity and vendors. So make sure your experiment is achievable with what like skill level and commitment level that your team is willing to put in, and for any materials that you need. So research ahead of time. Make sure all the vendors are that are able to offer this material is trustworthy, and make sure that you're able to obtain it when you need it. So if it takes like 2 months to ship from China or something, probably either look for another vendor or for like another material. And yeah, if you guys have any questions, like feel free to just unmute, or you can like type in the chat. Okay, cool. Let's move on then. Let me know if you guys have any questions. All right, so next is the design process. When you're building your mechanical and when you're designing it for the first time, and when you're iterating later on, this is the basic design process that you usually go through. So first, you define the problem. So what is it that you're trying to solve? And this may seem obvious, right? But define what you really want to achieve. And if it's valid and justifiable, then you start to generate concepts. So here you can even like look online for different inspirations. So if you're trying to solve a problem, likely a lot of the mechanisms will already exist online. So if you're able to find something similar to that and apply it to your own project, then that is a pretty good use of time. Otherwise, you can also generate your own concepts if you think of anything as well. And if the technology exists, then you can develop your solution. And developing your solution, like if you run into multiple solutions, you can use a decision matrix. And that is basically where you have all of your different, I guess, solutions like in a table, as we kind of did with the idea decision matrix that we did earlier for your experiment. And then for like each idea or each of the solutions, kind of look at whether it'll fit within the space constraints, whether it's easy to make, if it's prone to failure, all of those different factors, and use that to decide like which one you want to focus on developing first to save the most time. And then if that doesn't work, then move on to a different solution. And then so afterwards, you want to construct and test your prototype and evaluate to see if your solution works, and finally present that solution. If that works. Yeah, so some other tips I think that are helpful. When you're like making your design for the first time, I would say start with drawings on paper instead of using Google Slides or CAD or Tinkercad or something like that. Since we'll all be in person next Tuesday, I think it's a much better way to collaborate and also much faster to kind of like sketch down and to like communicate your idea across. When you're more set on what you really want to do, then you can use slides, whether that's for like presentation or for your own like reference. And then you can also use CAD if you need any like 3D parts, for example. But like drawings is like much less time consuming, and you're able to iterate much faster. So like when you're making it, also like keep in mind the space constraints, because you can only make it so big. Make sure if you're building a prototype that's big and you scale it down, make sure it still works. And another thing, it's okay to iterate. Like even engineers have to do this all the time, right? It's not like you'll get the perfect solution the first time you make it. Oftentimes, like you'll have to do it again and again, either with like completely new ideas or small adjustments. But it's totally okay to iterate. And even if you like send the parts to like the 3D printer and you have to print it multiple times, like that's okay. Everyone has to do that. All right, so here's kind of an example of kind of the engineering design process. So the problem that we're trying to solve here is to print a liquid helix in space. So it's kind of like a spring shape of a certain liquid. And you would think that is easy, but then this team found out that if you spin tubing across its axis, then that causes the wire to wrap around itself and eventually crimp, which means that the wire goes at an angle so that no liquid can flow through it. So we tried to solve that problem. And to solve that problem, we first generate concepts. So by looking at, I guess, examples of things that work in real life, we're thinking, so how can we solve this problem? And we know there's things called like decoupling mechanisms that basically help to like separate the spin of something from something else. We also thought of maybe ball bearings. If you put the tubing inside a ball bearing, then it can twist by itself. Or we could do something maybe with the rod of a train wheel, as the rod like only moves in a circular shape, then that might work as well. And so we start to develop our solution. We first choose the train wheel rod, and it kind of looks a bit like this. On the left, we used Google Slides to make our prototype. Of course, when we first started out, we did draw on paper, and then we drew it in Microsoft Teams, and then we put it into Google Slides. And then you can CAD out your design. So we wanted 3 or 4 different parts. These 2 wheels over here, and then this rod, as well as this, the small wheel over here. And so this was kind of our first prototype. And we printed it out and built it, and it kind of failed. And the reason it failed was because the rod in the perfect world, like this would work. If all the designs are like exactly, all of the measurements are very exact, then this should be able to turn around and rotate like a train wheel. But because of our engineering flaw, we realized this wouldn't really work. And so we had to iterate our design since the rod would get stuck at a diagonal position. So we iterated, and the second, or this was probably like the fourth iteration that we came up with this design over here. So this part has, you can see like this turning handle thing, and that kind of solves the problem of the tubing twisting around itself. And so that was our final prototype, and you can see like when you're starting out to build your prototype physically, you don't really have to use like the most professional materials, right? Like this here is some sort of wooden bead in the shape of a fish. And here is literally like blocks of wood that we epoxy together. So when you're building like a proof of concept prototype, you don't necessarily have to get it to scale at the very beginning, but as you know that your idea will work, then you can scale it down and think about how everything will fit in the chamber. And so this was kind of like our final design. You can see it's much more scaled down. The distance between the tubing and the fish and the motor is much smaller and more compact. And you can see like it fits kind of diagonally into the micro lab. So let me know if you guys have any questions. Okay, cool. Then let's. Yes, William. Okay, yeah. So from the legendary fellow William Tang, I think this is a pretty good summary of what we kind of talked about iteration. So your first design will not, cannot, and should not be your perfectly thought out final draft. You need to fail faster to experimentally work out the kinks in your hardware design. And sometimes like you'll have to redesign something multiple times. So use your brain, time, and effort when designing, but don't feel stressed to make it perfect. It'll come with time, and as you work on the idea, you'll slowly get the final prototype. All right, cool. So now that we're done talking about the engineering design process, feel free to let me know if you have any questions. Otherwise, we'll move on to block diagrams and mechanical plans. Thanks, King Shuck. Okay, so first off, what is the difference between a block diagram and a mechanical plan? A block diagram, as you can see here, kind of represents the relationship between your different components. It's not really to scale, not 3D, and sometimes it's not to shape either, so it can just be very representational and abstract. And if you need, instead of drawing out the entire block diagram for your entire experiment, there's like a part of your experiment that's pretty complicated. You can feel free to zoom in instead and just focus on that small part. So here are some examples on the left. This is from a previous year, if you guys know Vital, his microbial fuel cell experiment. And this kind of mostly shows their electrical parts actually. So you can see this is a microbial fuel cell, it's connected to 2 pumps. So here, like all of these represent, I guess, the items, components, and then these represent either tubing or wires. So that goes to all of these different parts. It goes to an amplifier. The microcontroller goes to a camera, an LED, and you can basically see like how this entire experiment is related with each other. Other times you can also have not to scale like representations of your chamber, as with this case over here. So if before like you CAD out your chamber, if you're interested in kind of figuring out where everything's gonna go, or like I guess like rendering it in 2D, here's an example. So this one, it's I guess more complicated from a normal chamber in that you have to allow for air displacement. Since otherwise, if you pump things into the chamber and nothing can get out, then you're just like increasing the pressure a lot, and your pump may not be able to handle that much pressure. So that's why this chamber has kind of this like balloony shape over here that helps the liquid to expand into the balloon. And So this basically like shows how this chamber would work here. Over here, this could be something that you also put in your experiment presentation that you give to the mentors, I think next week pretty soon. So if you have like any ideas that you don't really want to fully flesh out in scale, this would be a great way to do it. And of course, like you can always start off with sketches, and even in your like experiment presentations, you don't necessarily have to use Google Slides, I would say, as long as your idea is well thought out and the mentors can kind of follow along with what your experiment design is and how it will work, that'll all be okay if you want to use sketching as well. And finally here, this is an example of the fluid system block diagram. So see, this one includes the two pumps. It has the oil bag and it goes to the chamber, and it kind of shows all of these different check valves that allows the liquids to flow in these different directions. And it also has what each of these liquids contain and how the orientation moves along the different tubing. All right, and so now we get to mechanical plan. Let me know if you have any questions about block diagrams. But essentially, mechanical plans are 2D or 3D representations of your experiment design, and these should be to scale. So this should really show like how all of your components will fit together. So not only their relationship, but also whether you're able to place them all in the size of your tiny microlab. So for this, you can either use Tinkercad, Autodesk, either Inventor, Fusion, anything, or you can use basic Google Slides template. And I'll send you guys like a link of components and measurements that are already to scale, so you can just copy and paste that to use. And so I guess on the left here, like if any of you guys are interested in using Tinkercad, let me know. Wait, no, actually, yeah, this is Autodesk. So if you're using Inventor or Fusion, we do have ready-made files of the basic like camera and the microlab. So if you want to use a 3D CADing software to put all your parts together, you totally can. This is pretty time consuming, but if you want to do that, I can send you the template, just let me know. Otherwise, if you use Google Slides, so I think I would recommend using Google Slides because it takes much less time. You're interested, cool. I'll send you the stuff after this presentation then. But if you use Google Slides, this is basically what it would look like. These two examples are both made with slides, and it's a great way that you can collaborate with your team as well. So just like share the document and you can all work on it. I think there might be a better example here. Okay, maybe not. Okay, we'll talk about how to construct the mechanical plans later. But in terms of constructing your, okay, cool, we'll also send it to you. Thanks. And so in terms of constructing your block diagram, you guys can use just like Google Slides. You'll know like there are shapes in this section, right? And then you can add text to the shapes as well, put them different colors, and then you also have your lines and arrows that you can use. So this would just be a basic example. I'm sure all of your experiments will be at least a bit more complicated than this, but this is the basic idea. Like you have your viewing chamber, which your camera is like next to and should be looking at. You have your microcontroller, and of course, like these don't really signify necessarily the placement of everything in your module, but it does like signify the relationship. So for example, your LED has to be connected to your microcontroller, your camera has to be connected to that, and your pump has to be connected to your chamber and your controller. And so that would be what your block diagram would look like. And another example is here. So if you want a more like 2D representation, this is too abstract. Like often, if you just look at this by itself, you're not really gonna get what's going on. So if you want to create something else with Google Slides, more complicated shapes, you can make something like this. So in this case, like these two would represent pumps. This would be your chamber with Gore-Tex, which is kind of like a flimsy glove-ish type of material that allows that can expand for volume differences. And so you would have your pump on the left that's pumping one type of let's say nanoparticle or something, or dye, and on the right another type of liquid, and your camera's here. So this is just like another way of representing how your experiment could be placed. Okay, cool. Right, so next is mechanical plan construction. So this is a bit more complicated than your block diagram, obviously. So these would all be completely to scale. Luckily, we do have templates of all of the components that you will need, or most of the components that you will need. So all you need to do is like drag and drop around. Just make sure like if you're using any of these ready-made components right now, they are to scale. So try not to like change the scale, and by accident you can rotate and like translate it. And if you're making your own parts, there's also a ruler that's in one of the template slides, so you can feel free to use that as kind of like a reference. So you might also want to calibrate the ruler. So we'll show an example. Let me see. Okay. And always like let me know if you have any questions. Okay, so here's an example. So I'll send you guys all this presentation so you can access the template later. But this is what it would look like depending on what you need. Usually when you create a mechanical plan using this, you'll have both a top view and a side view. So this would be your top view. Here on bottom, this is your PCB, and this is where your camera would be. So be careful when you're placing stuff. Like you can place stuff on top of the camera, on the bottom of the camera, but there's not much space, so keep that in mind. And so your space extends all the way from this chip over here to this line over here. And this would be your side view, so you can see the camera here. And same thing as well, like your PCB goes from here to here. This is the camera chip if you need to measure like the dimensions of like the front view, I guess. Over here, let's get that one. Over here is just some examples of how you can like play around with your mechanical plan. You can see they have like these different pumps that they can layer on top of each other. They made their own parts, and these parts like they don't have to be complicated. You can use rectangles to represent all of your different parts, but just make sure like you know their dimensions are going to fit, and you label them well as well. And here are the pumps that you can use. I think this year we might have changed the pumps. I'm not sure if y'all are using the Takasago RPQ1 pumps, but the dimensions are very similar. Might not be exact, so you might have to change that a bit. But essentially you can use these parts and just like drag and drop. It also gives you like the specifications. So feel free to refer to that. And here are some more examples of mechanical plans. Yeah, so for pumps, usually we use one of two different types. It's either the Takasago pumps that we used to have for the majority of our experiments. Those run at 0.45 millimeters per minute, and this is the correct size for those. And the other type of pump is from some sort of Chinese manufacturer, I think. But it runs a bit slower, and also it's a tiny bit wider, I think. So I'm not sure. Wait, Mr. O, are you still there? Okay, I don't know. Oh.
Yes, I am.
Wait, do you know like which type of pumps we're using this year? Is it still Takasago or the other one?
I think it's Takasago that we're going with again.
Oh, okay, awesome. Yeah. Okay, then for the Takasago, yeah, then this is the pump that we usually use. And so I guess you can just use these dimensions then. Though if you do need like a pump of faster, slower discharge rate, one thing you can do is modify the electrical. And another thing you can do is, I guess, purchase another pump. But we'll go a bit more into that later. And so these are some examples of mechanical plans. So for this one, it's a bit simple, but you can see you have your pump over here. This would be your waste bag, so make sure to include that, or your liquid bag. And here is the chamber that you're going to use. And this is the displacement bag. And in side view, you have the same thing. You can see like here's a spacer. So how are you going to make sure that your chamber is aligned with the camera and that it's like in place and nothing's moving? And make sure to also like include your tubing and to get an idea of how it looked like. Here's also the front view. This is another example. So this might be more like when you're still CADing, when you're trying to figure out how big like your CAD stuff should be. You can take the ruler around, like drag it around to see if I want to make like this wheel, for example. This looks like, I don't know, 20 millimeters. So I would use that to kind of get an idea of how big my CAD should be before I actually print it out. And this is also an example of a like two directional module. What do you call it? But this is like if you have two modules that are like assigned to you, you can totally you have like a much larger space here. And this is the example of like a material injection chamber diagram that you guys saw earlier. So this is a block diagram. But basically, if you want to plan out your CADs here as well before you go into 3D and make it like much more, and it takes much more time, you can first plan it out, plan the dimensions out here. Yes, very innovative. Okay, so we'll send you guys that in a tiny bit. But for now, let's keep going and let me know if you guys have any questions at all. All right, cool. So this Tuesday, y'all will have something due. So the first ISS meeting, by the beginning of the meeting, try to make your two block diagrams of the two proposed experiments that you guys have. So the block diagram again is like the 2D kind of representation. So you can either do it like this, if it's like rather like easy to understand, or if you don't have that much time, you can first do it like this. But if your experiment is a bit more complicated, such that it's hard to understand from this basic diagram on the left, then you can do one of these on the right. And this is also using Google Slides, so you can use all of their like different shapes to create this as well. And so yeah, so just try to get your two block diagrams done. And I'll help to review some of your diagrams on Tuesday's meeting. And you can, it's a good idea to have these two diagrams in your experiment proposal presentation. So the mentors really want to see how your experiment works, and just by explaining it, explaining it with words, what the proposal is, like they're most likely not going to follow, since like it's pretty hard to understand without like visuals. So try to have these block diagrams. It really helps a lot. And like at the same time, these block diagrams also help you to see like if there's any problems in your design, and if all the components will really like fit together and like they're kind of their relationship. Cool. Let me know if you guys have any questions about the assignment. And if you have any questions later on when you're making it, feel free to text me on Teams or like text my Warrior Life account on iMessage. And so that's basically it on the like diagram side. Here's just some other mechanical info that it's pretty cool, and you guys can start to think about when you're creating all of your mechanical designs. First of all, if any of you guys are using liquids, I think a lot of the teams are this year. Here's basically how like peristaltic pumps work. So you can see over here, you're kind of taking the pump apart, but in its basics, the pump is just like a piece of tubing. For peristaltic pumps in particular, it's a piece of tubing that has a motor that's like kind of twisting the tubing and like I guess moving the liquid along while you're like I don't know how you say it, squeezing the tubing. So you have your motor here. This is the pump body, and these would be all like the rotating components, and you would have a piece of tubing through here that is being squeezed by this rotating thing. So for your conventional peristaltic pump, peristaltic pumps are basically like just squeezing And the reason we use this is because in gravity, you can't really rely on gravity on the ISS, right? And you don't want like gravity screwing with your results as well. So that's why we use peristaltic pumps, because it helps to squeeze and it doesn't depend on gravity at all. So conventionally, it would look like this. You just have like either 2 prongs or 3 prongs, kind of like squeezing the tubing together so that the liquid has to flow through. And there's like no backflow as well. If in the case of Takasago, they have a tiny bit of a different design. So instead of like 2 or 3 different contact points, they use a kind of weird shaft with a ring. And so when the shaft rotates, then your ring kind of squeezes the tubing at 3 different points. And so the fluid will keep moving because you're kind of creating like this vacuum that causes the fluid to flow through this tube. So when your pump is off, that also means that like if I pause this video right here, it means that no fluid can go forward, no fluid can go backward, unless the pressure that you put on the pump is so great that like your tubing, that stuff leaks past. But that's you usually like when you turn your pump off, then just the liquid will not move. And also, if some of you guys are using double pumps, I encourage you guys to check out the double pump module. What it basically is a 3D printed part that helps you to mount your 2 pumps on the 2 sides of your camera. And what that does is it saves you a lot of space, because otherwise your pumps are moving all over the place, and you're also placing it in other places where if you just put it like in front of the camera, then you can't really place any other components there anyway, left and right. So if you put it there, it does save a bit of space and also prevents it from like moving around. If you're interested in that, let me know, but that's just something to consider. It's probably too early now, but I can give you the CAD of that. And some other things to keep in mind for your pump. So the pump has some sort of silicon tubing, and that tubing does react with certain chemicals. So if you're using any sort of weird oil or something like that, probably try to test it with the pump tubing before like 3 weeks before your flight to see if it actually works. And also, because of the peristaltic pumps design, you can see like it does squeeze these liquids in bursts. Like when it goes around the circle, it's like burst here, then it stops, then burst, then it stops. So it does cause pulsations. So if you're looking for like a very steady flow of liquid that goes like this instead of like pulses, that's going to be very hard to achieve with your peristaltic pump. There are ways of reducing the pulsation if you connect it to some sort of very long wire that can kind of like absorb some of that pulsing effect, but it's very hard to get like a straightforward flow. So that's another thing to keep in mind when you're designing your experiment, if you need that. All right, and some of the last things, other fluid parts, we have barbed connectors and valves that you guys can use. So your tubing, your pump is connected to some sort of tubing, and for the tubing, if you want to connect it to other tubing, whether in like whether just like connecting 2 together or connecting 3 tubings together or something like that, we have all of these different connectors. So this one over here is called a straight connector. What it does is basically just connect two pieces of straight tubing together, or if you connect like your pump to a piece of tubing, you can also use this. Then we have the T connector, and what that does is it connects 1 piece of tubing to 2 pieces. So we just have like 3, I guess. And then we also have these T connectors, and this may save space because sometimes if you want your tubing to like twist around, you don't want to bend it necessarily. You can instead use this elbow connector over here that gives you kind of a nice 90-degree angle. And then we also have check valves. So check valves just help your fluid to only flow in one direction. So for example, if you don't want any backflow, if you only want your fluid flowing like forward, but you're afraid that it will flow backward and mess up some things, you can add a check valve. And how a check valve basically works is with a minimum like amount of flow in the correct direction, the valve will open and it will allow like fluids to flow past. But if your flow is not big enough, it won't let anything through, and that's kind of the bad part. But if any flow goes into the other direction at all, it does not allow anything to go through. So that's how you basically use the check valve. For these metal ones that we have, when you guys go to ISS on Tuesday, you can check them out. They have an arrow, and arrow just means it allows the flow that direction, but not the other way around. Some other plastic ones have this type of like symbol, so that basically means it's kind of counterintuitive, but it only allows forward flow in that direction, in the direction of the open mouth, and it doesn't allow any flow in the other direction of the arrow. So these are kind of different symbols that they use. And then finally, you have male and female lure lock adapters. These are if you guys need to use any needles and connect your needle to a piece of tubing directly, you can use this. So the tubing goes on this side and it kind of connects. It kind of looks like this T-barbed connector here, or this barbed connector. And the other side, depending on whether you have a male or female needle, so whether the needle's like spiral part is inverted or not, that will connect and twist onto the other side over here and over here. So you can connect a needle straight to your tubing. Cool. Okay, let me know if you have any questions about that. Otherwise, this is the last thing. So here are two different part catalogs. If you guys get stuck on ideas, especially any fluids ideas, here are two pretty good like catalogs of different mechanisms that you can use and perhaps order. So this has anything from like valves to I think pumps to all sorts of crazy stuff. It's pretty cool to look at. So when I send you guys the presentation, you guys can click on these two covers and that'll bring you to a PDF. This one is too large, so you do need to download it, but this one is relatively smaller, so you can just preview it straight. Though I would probably recommend using this one, Cosina catalog. And I think if you do find anything that's good on here, you can probably order it straight from Cosina. Or you can like search it up on Amazon. It might be a bit cheaper there. But these are like two catalogs that you guys can use if you ever like run into trouble designing like your experiment systems. Yeah, that's basically it. Let me know if you guys have any questions. I see some questions in the chat actually. Audiobooks. I have audiobooks for all of the research papers that you need. Okay, so liquid leaking. Yes, the pumps, they can endure a certain amount of back pressure, if that's what you mean. Sure, that will go. Yeah, so if the pump is off, then it usually does not allow liquid to go through. Of course, like if you apply enough pressure, then that's going to cause the pump to either rotate or your wire or your tubing to burst, or something like that, or for the liquid to go straight through. But like as long as you're not applying that much pressure, the tubing kind of acts like a plug, I guess. So yeah. A lure lock is kind of like a nail. So like you have the, how do I explain that? It's kind of like the inside of a bolt, inside of a nut, and like the outside of a nail. It's like that spiral shape that helps it to lock together. I'll send these slides out in an email a few minutes after this is finished. Yeah, let me know if you guys have any more questions. Oh yes, we should also invite you guys to the Discord. Yeah, so that's basically it. If you guys don't have any more questions, then feel free to leave. Thanks so much for coming. Otherwise, if you have questions, feel free to chat me. or like later as well. So thanks, y'all. And good luck on your block diagrams.
Bye. Thank you.
You
Thank you.
All right, thank you.
Thank you.